Dynamic compressors increase the pressure of a gas by using rotating blades to increase the velocity of the gas. Types include centrifugal and axial compressors. The following figure is the assembly drawing of an axial compressor. Axial compressors are used for high-flow, low-head applications, usually above 100,000 actual cubic feet per minute inlet flow. The most common application for axial compressors are air blowers for the fluid catalytic cracking units used for petroleum refining, or MTBE compressors, and gas turbine air compressors. A typical curve for an axial compressor, so the percentage volume versus the percentage compression ratio, is shown here. Notice here that the pressure rise from 100% flow to surge flow is always greater than the corresponding pressure rise for a centrifugal compressor. An assembly drawing of a multi-stage horizontally split centrifugal compressor is seen here. Recall that a centrifugal compressor can also be called a radial compressor because the exit flow from the impellers is radial as opposed to axial. A typical percentage flow versus head centrifugal compressor performance curve is shown here. As a comparison, the head rise shown here for the centrifugal compressor is approximately 10% as compared to 30% for the axial compressor shown in the previous figure. The principle of operation of a dynamic compressor always seems more difficult to understand than that of a positive displacement compressor. As discussed in a previous video, dynamic compressors increase pressure by using rotating blades to increase the velocity of the gas, as depicted here. Now take a look at the following figure. It shows the upper half of a centrifugal compressor impeller with the side plate removed. The velocity vector u is the blade discharge tip speed, and the velocity vector v relative is the discharged gas relative velocity. Simply stated, the characteristic shape of any dynamic performance curve, so rising head versus decreasing flow rate, is a direct result of the relative velocity through the impeller or blades. The higher the relative velocity, the less energy input from the impeller blades, and the lower the relative velocity, the greater the energy input from the impeller blades. If this concept is not crystal clear for you right now, then don't worry. We'll get back to it in later videos with more details. For now, let's get back to our simplified process system, but this time including a dynamic compressor, and then apply the same methodology used in the previous video for a positive displacement compressor. We will use the same set of pressures, but the flow rate and horsepower will be larger than that for the positive displacement compressor, since dynamic compressors usually handle inlet flow rates above 5,000 actual cubic feet per minute. So let's assume the inlet flow is 20,000 and the brake horsepower is 10,000. Let's plot the flow versus pressure ratio and the BHP on the appropriate graphs. The pressure ratio here is identical to the previous example, since the suction and discharge pressures did not change, and so is still equal to 4.45. So the first operating points corresponding to these conditions are plotted as shown. Now let's assume again that the control valve in the discharge process system is closed slightly. This action causes the compressor discharge pressure to rise to 180 psi. The horsepower, however, decreases to 6,000. Why is that? Because the characteristic performance curve of any dynamic compressor is different from a positive displacement compressor. A positive displacement curve is essentially vertical, since the actual volume flow is constant. Therefore, the brake horsepower will increase as the pressure ratio does. In the case of a dynamic compressor, increasing the pressure ratio will result in a lower compressor flow rate, since the only way a dynamic compressor can develop a higher pressure ratio is at a lower gas velocity, so lower flow rate. Simply stated, the longer the gas is in contact with the energy producer, which is the blades, the higher the pressure ratio. For a dynamic compressor, this means the flow rate must decrease. In order to see this on the graph, we need first to calculate the new pressure ratio. Recall that the ratio is equal to the discharge pressure divided by the section pressure, and both pressures must be expressed in absolute pressures. So here, the ratio, after doing the calculation, will be equal to 5.61. Now, plotting the higher pressure ratio and BHP point on the figure will yield a higher pressure ratio, a lower flow point, as depicted here. By observing these two curves, the characteristics of any dynamic compressor are as follows. Dynamic compressors deliver variable volume flow, have a fixed head capacity, and are self-limiting. As opposed to a positive displacement compressor, the dynamic compressor is self-limiting and does not require a relief valve to protect the compressor and driver. The next figure summarizes the characteristics of positive displacement and dynamic compressors by presenting their typical performance curves. Before to finish off this video, what I really want you to remember and to understand is that positive displacement compressors are not self-limiting. This means that the pressure ratio will continue to rise until the case pressure is exceeded. On the other hand, dynamic compressors are self-limiting. Their performance curves, as depicted here, show a decreasing head or pressure with increasing flow.